Hi, pre-calculus students. We are going to work on graphing logarithmic functions before you head out over the holiday, and hopefully this lesson video will be short enough that you can get all of your work done and have no math to think about when you are resting over the next 10 days or so. Our goals of the day are to be able to sketch logarithmic functions using these key points, 1, 0, and B1. We'll kind of bring those up as we go through the lesson. You should be able to identify or connect key features such as the domain, the range, the asymptotes, and the end behavior on the graphs of both exponential and logarithmic functions. So hopefully you'll understand how to tie the two graphs to each other, or how to use the exponential as an advantage to get the logarithmic function if you're not sure. And hopefully we'll be able to revisit and you'll be successful with describing transformations of logarithmic functions, again, using these key points of 1, 0, and B1. Notice this is a typo, so you need to cross that off and change that to 1, 0. Before we move on with graphing, I just want to remind you of what we learned last class, and that was the definition of logarithm. If we take log base b of x equals to y, then we know that the base to the power of y is equal to x. So remember, whatever this base is of the logarithm, you're asking yourself, what power do I take that base to in order to get this value of x? So what power do I take the base to in order to get this value of x? So we're going to use that idea. Remember, these are inverses of each other, and we are going to use that idea when we go to the next page and we start to graph. All right, so what are we going to do today? It says you learned yesterday that logarithms undo exponentials by finding the missing exponent. Today we're going to explore the graphs of these inverse functions. So we just talked about how logs and exponentials are inverses of each other. So you can see here it's asking us, the table below represents the function y equals log base 2 of x. Use the table to graph the function and answer the following questions. So just before that, I would love for you to just think about the inverse of log base 2 of x and graph that on there. So what is the inverse of y equals log base 2 of x? So hopefully you're saying, okay, the inverse of that would be 2 to the power of x equals y. So I'm going to graph that. So 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, 2 to the power of 3 is 8, 2 to the power of negative 1 is 1 half, 1 fourth, 1 eighth, etc. So just some key points we want to see here is that in this function right here, the exponential function y equals 2 to the x, what do we have? Well, it goes through point 0, 1. It has a base of 2, right? So it also goes through point 1, 2. It has exponential growth, so it's growing from left to right. It has a horizontal asymptote of y equals 0, right? So it goes through this horizontal asymptote here. The domain is all real numbers, negative infinity to infinity, and the range is from 0 to infinity, but it's exclusive of 0 because of that horizontal asymptote. It's going from 0 to infinity. So hopefully now that you know that, and you know that logarithms and exponentials are inverses of each other, and inverses just swap those values, right? The x and the y just switch places. So let's see what happens. The other thing about an inverse is that they are reflective over the y equals x line. So this log base 2 of x equals y should be reflected over that yellow line, the y equals x line. And then we should see, yeah, then we'll have the graph. So you can use the table, or you can use these points I made. If we use the table, we go to the right 1 fourth, down negative 2. We go to the right 1 half, down negative 1. We go to the right 1, up and down 0, to the right 2, up 1, to the right 4, up 2. We go to the right 8, up 3, etc. So now, because they are inverses, you can see that it is reflective over that yellow line that I drew. that these ordered pairs did switch. So this ordered pair now is 1, 0 instead of 0, 1. This ordered pair is 2, 1 here, right? It's the 1 and then the base. But now it's going to be the base and then 1. So we go right the base amount and then up 1 unit. You can go right the base squared up 2 units, right the base cubed up 3 units, right the base to the fourth up 4 units, or you could think about that inverse function of its exponential, switch those ordered pairs, and here you'd have it. So following up these questions, number 1, it says what value of x would produce an output of -5? So log base 2 of what value would produce -5? So in other words, 2 to the -5th is equal to 1 over 32. So this would be 1 over 32. How do you know? Well, I just showed you. So what's going to produce a -5 here would be 1 over 32 if I were to extend my table over here. Why? Because 2 to the -5th is 1 over 32. What is the domain and range of this function? Well, remember, we just did the domain and range of the exponential. These are inverses of each other, so the domain and range should swap. And let's see if that happened. So yes, in fact, the domain does now go from 0 to infinity, right? It's just from this right-hand side of the graph. We don't include 0 because there's a vertical asymptote there. So we have a vertical asymptote at x equals 0, where before we had a horizontal asymptote of y equals 0. It didn't ask for that, but we're going ahead and talking about it. And then we also want to know the range. Well, what is the range? Well, hopefully you see that that is all real numbers. So from -infinity to infinity, or you can put the all real numbers symbol. Sorry, tricky for me to say. Okay, so there you have it. You can see they're inverses of each other. Really, it was only asking for this portion right here, but hopefully you're making the connections with the inverse, which is 2 to the power of x. So how are your answers to question 2 related to the domain and range of this? Well, sorry, I ruined that for you. They are inverses, therefore they swapped. So the domain of 2 to the x is the range of log base 2 of x, and the range of 2 to the x is the domain of log base 2 of x. Okay, so let's look at the next part. It says the graphs of 3 parent logarithmic functions are shown below. What do all of these graphs have in common? So hopefully the first thing, or one of the things you're noticing, it doesn't have to be the first, but all 3 of them go through point 0, or sorry, 1, 0. Oh my goodness, I'm struggling here. They go through a point 1, 0, right? So we see that. Hopefully you say they all have a vertical asymptote at x equals 0. That's also true, right? They all have this vertical asymptote right here. And they all increase as x goes to infinity, right? So they all increase maybe slowly, is what you're noticing. It's not super steep, it's just going to be a slow increase as you go to infinity. Part B, the equations for the 3 graphs are log of x. Remember, when there is no base, that means there is an invisible base of 10. Right? So log base 10 of x, then we have log base 4 of x, and then we have ln x. Remember, ln has a base of e, and e is about 2.718. So which is which? How do you know? Well, we were just talking earlier or on the previous part about the significance of B1, right? So if you go to the right, the base, and you would go up 1 unit. So notice here, sorry, I've written on this, but you have your y-axis, right? So your y-axis is going up by 0, 0.5, 0.1, 1.5, 2, etc. But I'm looking for this point B1 because they all go through 1, 0. So for log base 10 of x, it should go through 10, 1. So if I go through the right 10 and I go up 1 unit, oops, I used the wrong color. What do I notice? Well, that would be right here. So this first one here is y equals log base 10 of x. The next one, if I go to the right 4 units and up one, so I went to the right four, the base of 4, and I went up 1 unit, I can see that's my blue graph. So this is y equals log base 4 of x, which means my green graph must be log ln of x. So what do I have? Well, if I went to the right 2.78 something and up one, yeah, that looks about right. So that's an approximation. You're not going to have a grid line or grid corner for the ln graph. So that's how I know. You also might notice that the higher the base, what do you notice about the turn through 1, 0, right? So this is a base of 10, this is a base of 4, this is a base of 2.718. So the larger that base on the logarithm, the tighter the turn and the slower those values increase, right? So the smaller the base, the yeah, or I guess it's easier to say the larger the base, the tighter the turn. Use the graph to estimate log base 4 of 6. And what does this answer mean? So go ahead and do that. What would you get? So I'm looking at my blue graph, right? So log base 4 of 6. I'm inputting the value of 6 for my x coordinate, and I'm going up to see what this value is. And I'm going to say that's about 1.3, 1.25. I don't know. You can decide. I'm just going to put 1.3. Okay, great. So log base 4 of 6 is about 1.3. That doesn't really tell my brain much unless I convert it. Hopefully, you're instantly converting it into exponential form. What does it mean? It means that if I take 4 to the power of 1.3, that should give me 6, around 6. How do I know that? Well, we could use a calculator and see if that's true. You could just plug in log base 4 of 6. But you know that 4 to the 1 is 4, 4 squared is 16. So 6 is somewhere in between 4 and 16. It's closer to 4, so that means, yeah, it's probably going to be that that does make sense. So I think that, yes, it is about 1.3. Okay, now we're moving on to transformations. So it says, suppose we shift the function y equals log base 4 of x to the right 3 units. So remember, when you're going to the right, that's a horizontal shift. So when you're doing something horizontally, you need to work with the x coordinate, or that, because that is what's going to move left and right. So what am I going to do? Well, g of x equals log base 4. This is my x right here, so I have to manipulate that to show that it's moving to the right 3 units. And hopefully you're reminding yourself that you always do the opposite when it's horizontal. So if we want to move to the right 3 units, then I must make sure that I have this minus sign in here. And so I should have log base 4 of x minus 3. Now, what happens when I make that transformation to the right 3 units? Well, that is going to impact the x-intercept. It is going to impact the asymptote, and therefore it will impact the domain. But does the range change? My y values will not change. So that's the only thing that does not change. So I would say pause right now and see if you can figure out what is happening with the x-intercept, asymptote, domain, and range. All right, so is this what you've got right here? So remember our original function. If it was just log base 4 of x, it went through 1, 0 because 4 to the 0 power is 1. It has a vertical asymptote at x equals 0. That y-axis is my vertical asymptote. Therefore, my domain went from 0 to infinity, and my range went from negative infinity to infinity. If I move it right 3, I'm going to take this point 1, 0 and move it right 3. That means I'm going to add 3 to the x coordinate, so it becomes 4, 0. I'm going to take this vertical asymptote and move it to the right 3 units, so I'm going to add 3 to 0. So now I have a vertical asymptote at x equals 3. Therefore, my domain is starting from 3 and going infinitely to the right. So it goes from 3 to infinity, exclusive here. And then your range is the only thing that does not change. If you're not sure about this, then go ahead and graph it on Desmos so you have a better visual of what is happening. So here are your key takeaways you might want to write down. We have that parent logarithmic functions. Um, if their y equals log base b of x, then your base must be greater than 0. It cannot equal 1. So that's that blue graph right here. This is your logarithmic function. Remember that logarithmic functions are inverses of exponentials. Therefore, they reflect over this y equals x line, or every ordered pair. 0, 1 switches to 1, 0. So the x and y coordinates switch with each other because they reflect over y equals x. So y becomes x and x becomes y. And then what are some key features of a logarithm? Well, it goes through points 1, 0. It goes to the base comma 1. Why? Because that's true. The base to 0 power is 1. Base to 1 power is the base. It has a vertical asymptote instead of a horizontal asymptote. So vertical asymptote at x equals 0. Therefore, the domain is from 0 to infinity. And the range goes from negative infinity to infinity. So use this information to try to check your understanding. And then if you are not sure about the check your understanding, you can come back and listen more to this video. So if you look at this graph, it says graph f of x equals log base 3 of negative x without a calculator, and then identify the following. So I'm just going to get you started. This negative x, maybe that confuses you. So let's talk through it a little bit and then you can try it on your own. What does this negative x do? Hopefully you know what that is, a reflection. And when that reflection is paired with the x, you know it's a horizontal reflection, which means it's reflecting over the y-axis because this is horizontal, right? Going from left to right. So that is a reflection over the y-axis. So go ahead and pretend that you were graphing log base 3 of x and then reflect all of those values over the y-axis and see how you end up. So pause this now and then you can come back and check your work. Okay, so is this what you have? Hopefully you have the vertical asymptote being the y-axis, which is x equals 0. It was going to go through 1, 0, but we reflected it to make it go through negative 1, 0. It was going to go through 3, 1, right? That base, comma 1, but we reflect it, so it became negative base, comma 1, so that was negative 3, 1, so it's going through this key point here as well. Um, then what is my domain? My domain is negative infinity to 0, and then my range is just going from negative infinity to infinity. So hopefully you got these two key points at negative 1, 0 and negative 3, 0. As we continue through the check your understanding, I would encourage you to pause and attempt 2 and 3, and then unpause to check your work, or you can look in the answer key as well if you feel pretty confident about it. Otherwise, if you're confused, you can listen to the explanation. Okay, here are the graphs. Hopefully you're just doing it by sight. You're looking at the reflections. There were two vertical reflections, no horizontal reflections. So you can see my blue one here had a vertical reflection. This yellow one had a vertical reflection. So the two that had vertical reflections are these two. One you can clearly see going through the x-axis. So there's no shift upward here. So this one's going to be letter D, and this has a shift upward 5. So the whole thing got shifted up a little bit. So you can't see that intersection point. But it would eventually intersect. But yeah, this is B. This is D, just based on what we see with those graphs. Everything's the same except for this plus 5. C, there's only a vertical dilation. You can't necessarily see that stretch because there's no numbers, but there's no shift left or right. So my vertical asymptote going through the x-axis. A, it's shifted to the right, so I'm looking for a vertical asymptote that's shifted right 5 units. So it's got to be this one here. And this one's going down. That's not associated with the x. The x has to be in parentheses. This is right 5 units. This is up 5 and down 5. So here I'm looking for that typical logarithmic curve. Here I was just kind of reminding myself the typical log goes up and to the right. If I reflect over the y-axis, it's like this. If I reflect over the x-axis, it looks like this. Those are rough sketches. Sorry, it's not great. But here, this was moving down, just a normal log curve, except it moved down. So that's why this is E. Okay, then let's look at this last question. Write an equation for a logarithmic function that has a vertical asymptote at x equals 5 and goes through point 11, 1. So I just wrote the basic log y equals log base b of x. So we don't know the base, but we do know there's a vertical asymptote at x equals 5. So if there's a vertical asymptote at x equals 5, then the first transformation I can do is I can shift this to the right 5 units. So how do I take care of that? I just move this vertical asymptote to the right 5 units because it's usually at 0. So to make it right 5, now I have this as my new logarithmic function, but I still need to find my base. So how do I find my base? Well, I use this point right here. And when x is 11, y is 1. So I'm going to plug that in. So 1 equals log base b of 11 minus 5, and I'm going to solve. So that's 1 equals log base b of 6. So b to what? The first power equals 6. So what is my base? My base is just 6. So my equation for this to satisfy that has a vertical asymptote at x equals 5 and goes through point 11, 1 would be y equals log base 6 of x minus 5. So it's unfortunate that this is a B and that's a 6, but yes, this is the letter B. That equals 6. That's how I found my base because I used this point and plugged it in. Hopefully that helps. Good luck with the homework. I hope you are very productive during class and have a lovely holiday. And I'll see you in a couple weeks, about 10 days. Bye.